Okay, so I'm back. The time is currently 1:35 p.m. I finished the exam about an hour and a half ago. I've been relaxing in my room a little bit, but I thought I'd get this video out before I forget. So yeah, as you can see from the title, real analysis exam that I just did. Um, this wasn't too bad actually. However, I did take a bit of a gamble that kind of didn't work in the end. But first, a quick look at my cheat sheet. And I'd say me being lazy with this cheat sheet probably cost me more than any of the other exams I had. Yeah, see we got here some epsilon delta definitions. I didn't use most of this stuff. Ratio test or comparison test versus convergent or divergent. Um, what the right hand and left hand limits. Finding a recursive limit. Kind of thing. An example question for the limit of a sequence, proving the limit of a sequence. A couple definitions here. Alternating series theorem. What else? Unique limit. I don't even know why I wrote that, honestly. Cauchy sequence definition. And then another example question here. This one's a bit more empty. Yeah, some harmonic series stuff. Whatever that notation is, didn't even come up. A theorem there. Oh, I probably could have used that actually. Oh well, could have. I don't know, but so you got here squeeze theorem proof. I don't know even wrote that. Differentiation, more continuity, extreme value theorem, intermediate value theorem, that theorem, and then here's something I scribbled on just because I realized at the last minute that for algebra of limits, it's just for limits, not for convergence, which is a mistake I was making a lot throughout the year. And I only realized that because, it's only for limits, not convergence. But it can be used that if algebra of limits shows that an does not go to 0, then an diverges. But just a good little tip there. But on with the exam. Okay. So yeah, for the sets, determine the infimum, supremum, minimum, maximum. Okay, they don't exist. This wasn't too bad. Yeah, so for this one, minimum and the infimum is -1. There's no maximum or supremum. Wait, no, there definitely is a maximum or supremum. Oh wait, what did I say for that? Okay, I think I actually messed that one up. Oh dear. Yeah, so I'm thinking about it now. It seems like the minimum and the minimum and the infimum is -1. Supremum and maximum is 1. Oh well. This one, yeah, again, this is just really just the image of this. There's no maximum or minimum, so there's no infimum or maximum, that kind of thing. Saving this really not too bad. Here, find a set X such that the set Y has a minimum but not a maximum. This one I realized you can't really just choose like a finite set of numbers, because then it will have both a minimum and a maximum. So I made X equal the set of all natural numbers, because the set of all natural numbers is bounded below but not bounded above. So yeah, there's that. Use induction to prove So you're kind of just like an extension of the triangle inequality. Not too bad, honestly. I feel like I could have been a bit more like explicit, or is rigorous the word? I don't know. I'll say explicit because I feel like that makes a bit more sense. But I could have been a bit more explicit in the steps I was using. But I think I got the general idea. So I may have lost like 1 mark max because I wasn't being exactly clear enough with what I was doing. But I'm pretty sure I got most of the marks there. That one was fine. Just if these are all greater than 0, then it's an inequality. All right. So yeah, so page 1 not too bad, honestly. That would be worse. Page 2. So use what you just proved to show this. So yeah, this wasn't too bad either. Of course, take the modulus of these individual terms here at the top, and since sine and cosine, their max values are 1, Then it's bounded above by, of course, this becomes 1 plus 2 pi plus e over 2, which is all over 2, which is just that. So yes, not too bad. This one, I actually didn't finish this question because I realized I was going about it the wrong way. So originally I tried saying that, okay, when this is less than 0, it becomes the negative of this. Okay, yeah. Okay, so first, hold on. It gives the hint of sub in y equals x squared. So I did that. You get 3y squared minus 4y plus 3 equals minus y cubed. That's fine. And then I tried saying that when this left hand side is less than 0, this is like it's the negative of this. If that makes sense. So then it becomes a minus 3y squared plus 4y minus 3. And then of course when it's positive, it's just that. I tried doing that, didn't really get anywhere. So I just skipped it. And then when I came back, when I had like 2 minutes left, I realized, hold on, if I just, this left hand side is always going to be either greater than or equal to 0, and this right hand side is either going to be less than or equal to 0. Now, if I just show that these two are never 0 at the same time, then I've done it. And I didn't get down to writing it, but yeah, that's what I would have done if I didn't run out of time there. Oh well, though. Consider the sequence an equals 1 over n. Determine the first 5 terms of the subsequence. So you just sub in k equals 1, 2, 3, 4, and 5 into here. Then that will give you your n. Sub in those n numbers into there. You've got that. Hence or otherwise evaluate the limit of the subsequence. Of course, the limit of a subsequence is the same as the limit of the sequence. So it's, yeah, just, it goes to 0. Okay, here, consider the sequence Bn, where Bn equals that. So that Bn tends to 3. Okay, so for this question, I know I had to use I used the epsilon definition of convergence. If I've just got it here, where is it? Turn this on maybe. There we go, it's better. Here, yeah, I used that, and by manipulating that with the limit 3, I got the n like epsilon to be greater than 2 over epsilon. That seemed a little bit too simple, but like my thought process was minus 3 from this, right? Then you get just the mod of this part here. Then the mod of that is just 2 over n. And then, of course, you just get n, 2 over n is less than epsilon, so n is greater than 2 over epsilon. I didn't really know what else I could do there, but yeah, that's that there. Again, second page wasn't too bad. A bit of a mishap here, but not a bad question though, honestly. Alright. Okay, this question was fine as well. There was one tricky part that was just me being an idiot. So, yeah, let Cn be the product of these 3 functions here. Then use sandwich theorem to find, yeah. So for this, I just said cos ranges from -1 to 1. Therefore, we can have this as a lower bound of 5 over 2 minus n squared over n cubed is less than or equal to this, which is less than or equal to 5 over 2 plus n squared over n cubed. And as n goes to infinity, n squared over n cubed goes to 0. Therefore, this goes to 5 over 2. That was fine. This one, I tried doing ratio test with the limit with a 7 over 3 inside here, and it got so messy that it took me forever. So what I ended up just doing was I just took the 7 over 3 out of this limit because it was a constant. Because it's a constant, I thought to myself I could just do that. And then I should ratio test on this. I got that this I ended up getting that this goes to 0, which means that this limit goes to 7 over 3. I think I can do that. I'm pretty sure I can, but hey ho, we'll see. And then part 3, evaluate this. This was fine. Algebra of limits. Of course, divide every single term here by n to the 7. You get 1 plus 1 over n cubed plus 1 over n to the 5 plus 3 over n to the 7, then 2 plus 1 over n to the 4 plus 9 over n to the 7. Yeah, as n goes to infinity, that just goes to a half. Wasn't too bad. And of course, for this one, as Cn is just the product of these three functions, all you have to do is multiply their limits to find the limit of Cn. So then you get a half times 7 over 3 times 5 over 2. Gives you 35 over 12, I believe. So yeah, that wasn't... The question was, I'm quite happy with this question. This took me like a page to do because I kept messing up doing ratio tests with the entire thing, so I just split it up. But other than that, it wasn't too bad. Okay, question 4. Assume that AN, BN, CN, and DN are four Cauchy sequences. Prove that the sequence EN is also Cauchy. Actually, in a like revision session for this exam, we had the question just like this, but like it was a lot harder. But it was the same kind of principle. You just say that the sum of two Cauchy sequences is also Cauchy, therefore AN plus BN and CN plus DN is also Cauchy. Then you say that the difference between two Cauchy sequences is also a Cauchy sequence, therefore AN plus BN minus CN plus DN is also a Cauchy sequence, therefore EN is Cauchy. Okay, those are the first 50 marks of the paper. Not too bad, honestly. Question 5 hit me like a brick, and I don't think it's a hard question. It's just these kind of questions I'm not exactly the best at regardless. So yeah, as you can see, a little bit determine whether each of the two following two series converges. Here we go. So yeah, they're not even bad series themselves. It's just these kind of questions are so not my forte. I had no idea. I was thinking of trying to base this off of the harmonic series because I kind of got that idea from it, but I really didn't know what to do. Apparently, there's something in the lecture notes that explicitly tells you like what this whether this is convergent or divergent. I think they said that this is divergent. That's what my friend said, at least, that this is divergent. And this one, I can't remember what people said. Somebody got convergent, but from what I know, they just put this k of power while trying to expand it. They put this power of k like over the half and over the 1 over k, as in a half to the power of k plus 1 over k to the power of k. Of course, not how powers work, so I don't know if you can do that. But yeah, I'm unfortunate. And then, yeah, I don't know if I said or not, but I took a bit of a gamble in this exam, preparing for this exam, thinking, okay, because we've got this sheet here, it's unlikely that they're going to ask us for proofs because we can just write the proof on our sheet. So I didn't write any proofs on here. But think about it now, it's purely because I was too lazy to, not because I was trying to, get some sort of advantage over the lecturer. I was just being too lazy. And well, as you can see there's a proof question right there. I did start it off by saying that a series converges absolutely if the absolute value of the series tends to 0. Then I said that like let AN be a series that converges absolutely. Then I used like the definition of convergence again. But that ended up with just me getting like the absolute value of the series is less than epsilon. Now epsilon is greater than 0, so that kind of didn't really work. My friend showed me the proof that they wrote down on their sheet. It had something to do with partial sums, which is fair enough, to be honest. I would have never like figured that out myself, so oh well. So yeah, I've lost these 15 marks, guaranteed. It's out of 100, by the way, if you didn't know. Now, 6b. This one I was actually quite happy with because it reminded me of a harmonic series in the sense that the max value of sine n is 1. So this this here has an upper bound of 1 over n squared. And for a harmonic series, if the power, where is it? Where did I write it? Oh, okay, hold on. Okay, yeah, there it is. So if the power is greater than 1, then it converges, of course. 1 over n squared, that converges. And therefore, by the comparison test, this converges. So I was happy with that. Okay, and then question 7 actually was okay, to be honest. So yeah, define a function that maps real numbers to real numbers by this. For each n is a natural number, show first that the limit as x goes to 0 of x to the n sine x equals 0. So yeah, I just said that since sine x ranges from -1 to 1, we can bound this with a comparison test of with the lower limit of minus x to the n, and then less than or equal to this, which is less than or equal to x to the n. And of course, for minus x to the n and x to the n, as x goes to 0, the function goes to 0. Therefore, this also goes to 0. Simple 2 marks. Prove that f is continuous. So yeah, it wasn't too bad either. I just said that for x is less than or equal to 0. I said that for x is less than 0. I said that 10x cubed is the product of two continuous functions, 10 and x cubed. Therefore, 10x cubed is also continuous. For x equals 0, I showed that the right-hand limit, so the positive limit, and the negative limit as x approaches 0 from like both sides is the same. Of course, plug in x from the negative side into this function as it approaches 0. You put 0 into here, you just get 0. And then for here, to show that this goes to 0, I just use squeeze theorem again. So yeah, I think I said that like 0 is less than or equal to x squared sine x, which is less than or equal to x squared. Of course, x squared goes to 0 as x goes to 0, so that does as well. That's how I proved f is continuous at 0. And then for greater than 0, what did I do for that again? Let me see. I remember actually like putting. What did I do again for greater than 0? My mind is blanking right now. I don't think I used a definition. I don't think I did. I think it might have been squeeze principle. Wait, no. Oh no. Yeah, again, I just said that's the product of two continuous functions. Therefore, it's also continuous. Yeah, I remember I said that. Okay. Now, first that was say therefore it's continuous or no. That was all right. C, determine the points for real x at which f is differentiable. Remember, after I did this part of the question, I got that f is differentiable everywhere, which makes sense because these are two differentiable functions. But I thought to myself, the wording, the points, kind of implies that there are some like points where it's not differentiable. But I thought to myself, my gut's telling me that it's differentiable everywhere, so I'll stuck with that. Now, question 8. Let's really digest this. Let f be a continuous on the closed interval a and b, and differentiable on the open interval a, b. Suppose that f dash of x is greater than or equal to 0 for all x in a, b. Prove that f is increasing on the closed interval a, b. Hint, use the mean value theorem. Now, when reading this and I read the hint, I realized that I did not write the mean value theorem onto my sheet, which made my heart quake a little bit because I didn't know how I was going to do this. But I remembered like the main part of it, of course f of b minus f of a all over ba is equal to f dash of psi, I think that's what the symbol is. That part, the main part I was like worrying about was like the conditions for it. But I looked at this here, and I thought to myself, okay, I remembered it being something about being differentiability on an interval, and I said that okay, I'm going to I thought to myself, okay, if f is differentiable on this interval here, that means it's continuous on the interval as well. But seeing as the mean value theorem has f of b and f of a, that means it must also be continuous at a and b. So this must also be another condition for it. So I just said, okay, this must be the condition for using the mean value theorem. It must be there. So I just copied that down and said that mean value theorem states that, of course, f of b minus f of a over b minus a is equal to f dash of epsilon. And then I said, okay, since for f dash of x is greater than or equal to 0 for all x, that means f dash of psi, sorry, is greater than or equal to 0, which means that f of b is greater than or equal to f of a. Okay, so then I'd prove that at b f is greater at b than it is at a, but I realized I hadn't proved it for like the actual interval itself. So then I took another interval inside a and b where I said what did I say? Okay, yeah, I said I took another variable y, let to y be an element of the open interval c and x, where c is less than where a is less than c, which is less than x, which is less than b. So you kind of get an open interval inside this open interval here. I did that again for y, x, and c to show that it's increasing all over this this interval, because if it's true because since x applies to all parts of this interval, if I show that f of x is greater than f of c, like where c is the lower limit of this new interval, then it's increasing all throughout that interval. I think that's how I wrote it. I think that is how it works. I'm hoping that's how it works, because I felt like a genius writing this down, to be honest. But honestly, if it's not how it works, then I think I made a pretty good attempt at it. I might actually rewrite my proof like later on today or something and post it in the community tab, just so you guys can see it. But yeah, I'm guessing if there's like any, I don't know, like professors or PhD students watching this probably seems really easy for those guys. So yeah, but this one, bit of a struggle, but I got there in the end, I think. This one wasn't too bad, just proof by contradiction, honestly. So yeah, I just said assume that is less than that, and then you end up, by rearranging it and getting it all on the same side, you end up getting that 16x is greater than or equal to 48 for all x is greater than or equal to 0. That's obviously not true. When x is 0, then that's clearly not true. So yeah, man, that was this paper here. Yeah, these 15 marks here, question 5 and this one here, I definitely lost those, but can't do anything about it now. Other than that, I'm happy with how it went, especially with this question here, because I didn't even have this theorem on my sheet, so being able to like remember it and then also still do this question, I felt amazing. So, but yeah, the next video I upload will be about the hardest maths exam I've ever taken, which is the Oxford Maths Admissions Test. That should hopefully come out next couple of days, probably, I'd hope. So yeah, but that's all for now. See you next time.